So another syntactic parsing, like dependency parsing, that I've created playlists for dependency parsing, 3 lectures up to now, is constituency parsing. So, for example, there are 2 syntactic parsing methods, paradigms or problems, let's say, because it's a problem. Because constituency parsing is different than dependency parsing. So if you watch my playlist for dependency parsing, 3 lectures, you will see that it is different from my current lecture, which is about constituency parsing. So one morning I shot an elephant in my pajamas. How he got into my pajamas, I don't know. So this is a great reference from Daniel Jurafsky, this book. And if you look at the chapter 13, it's just about constituency parsing, which is a very important part of syntactic parsing. So dependency parsing is very different from constituency parsing, but you can use similar techniques and algorithms. Just like any other parsing, you can use, for example, we have dependency parsing, we have constituency parsing, we have semantic parsing, we have discourse parsing. But all of the techniques here that I explained, you can share. You can use one for another. I mean the algorithm, not the problem. That's the beauty of that. And all of them are either transient-based methods, graph-based methods, use pointer networks and so on. And but each of them has its own problems. Some of them have lots of computational complexity. Some of them are not, and therefore are not scalable. Some of them have problems that they get into local optimum, and it is bad because we want to reach the global optimum. But there are several, exponential number of local optimums. So this is an example of dependency parsing, and this is an example of constituency parsing. For example, you see, you go from top to bottom. So there are 2 paradigms to answer all of these questions. You either go from top to bottom or bottom up, bottom to top of the tree. So here, for example, we want to break it into 2 ones. So we are going from top to bottom. And then this, you break it again, and then just like a fractal. You break something again, some rules again, you go to deeper, and until, so you have lots of scales, like wavelet, you have lots of scales. You go deeper, you focus more, and so we have context-free grammar rules. For example, a sentence could either be separated into noun phrase and the verb phrase. It could also be separated like this: auxiliary, noun phrase, verb phrase, or it could go to, it's just a verb phrase. So there are 3 possibilities. There are different possibilities. And so we have this grammar. It is good. So of course, Noam Chomsky, the father of linguistics, and therefore he used a different kind of normal form. He defined normal forms in his books, hundreds of books he's written. But we don't need to just say we should obey the normal forms, because in artificial intelligence we are free. We're free from any rules. So we can create even one node can go to 3 instead of 2. So it may not be binary. So this is more general. I like it. There is no constraint or limitation. And so there are some types of grammar, but the constituency-free grammar is here. Context-free grammar is here. And then at the last layer, it is unrestricted grammar, type 0, unrestricted. And so recent parsers no longer have explicit grammar production rules, but it still use information about other predictions. So the lexicon, when we say lexicon, it means that a set of rows, each row has some, for example, determinant goes to all of the determinants, that, this, a. For example, noun goes to all of the nouns in the database, book, flight, meal, money, and etc. So this is the idea of lexicon. And the structural ambiguity, because you have different ways to parse this, constituency parsing, different ways. So, of course, we have several ambiguities. One of the most important is structural ambiguity, as you see here. So if you pay attention to man, with, so we have a different parser. But if you pay attention to saw and with, then you have a different parse. You have a different tree. Another example, you could pay attention to different things, so you have a different parse. And another example, the first example. And so there are two methods for syntactic parsing. You either do top-down parsing or bottom-up, two different in philosophy. For example, in top-down parsing, you could either use naive approach, enumerating all of the brute force. It's bad. But we use dynamic programming instead. It's much better. Of course, it has its own limitations. The second philosophy is bottom-up parsing. You either enumerate again brute force, or you go dynamic program, a little bit better. There are two methods for syntactic parsing, but the pros of top-down parsing is interesting. Never waste time exploring trees that cannot result in a sentence. But let's pay attention to the cons only, because we want to write an article that improves these ideas. We want to improve these ideas, so we should know the limitations. So the cons of top-down parsing is it spends considerable effort on trees that are not consistent with the input. So waste of time. But in bottom-up parsing, another problem, it generates many trees because you are going from bottom to top, many trees, many trees, subtrees that cannot result, but finally dead end, because you cannot continue, cannot result in a valid sentence. You cannot generate something that it is in our rules of product grammar. So the CKY algorithm, after you create it and store it, and finally you do this simple algorithm. And the probabilistic context-free grammar, as I said, each one has its own probability. For example, nominal to noun, or nominal to nominal noun, nominal to nominal PP, each one has its own probability, but this one, for example, is higher. So you can use these as well. So let me explain this beautiful article. What's going on in neural constituency parsers? So we want to assign score to every tree. And then we have a score. We want to maximize to see which tree has higher score. And the score of a tree is just the summation over all scores, over all edges and labels. So multi-layer perceptron span classifier consists of two fully connected layers with ReLU nonlinearity. So span representation is like this. We need a score. Here you will see that we want to maximize this. So finally, this is our training. We want to maximize this score. Of course, we consider this constraint as well, because we know the goal answer. But so we want to maximize the score. And we have an LSTM. So we write different words, tokens, and then we separate it, and then the stop token. So start token and stop token and our words between. So because we are using bi-LSTM, bidirectional LSTM, you can use forward and backward. And then using these, we create our own features, because at the end of the day, you need your own features to be able to give it to the input so that you maximize this S. So you should learn these weights. Of course, you have some bias as Z1 and Z2. And so after learning these weights, you can have this score. I use silence so that you can focus and less distraction. So you have your scores. And then you have inference. Even though our model operates on n-array trees, we can still employ CKY algorithm for efficient globally optimum inference by introducing empty label null with Sij and null is equal to 0. So the score of empty label is 0 for any pair that you say, any INJ. And INJ, of course, the span. For example, here, S1 through F4, this is span of 1 through 4 is 1 through 4. It means played soccer in. Played soccer in. So this is the span. So for any span, we have a score. And of course a label, because we are parsing, going from bottom to top, or top to bottom, depending on your architecture. And so this is the span. But we have an interesting thing, because we can go from bottom to top, because if we know these low-level things, but at the bottom of the tree, we can construct and go to the higher levels, higher span, bigger spans. So this is a smaller span, because what is a span from I to J? But we can separate it. Here is K. So this is one span, this is another span. And depending on where the cursor is going, K could be here, K could be here, we don't know, K could be here. For example, if K is here, then our span becomes this one and this one. So that's why we can say that the maximum of this span, of score of this span plus this span, is a good definition for a span of the overall system. Of course, we add for the INJL as well. So this beautiful law is the main inspiration for more than 50 articles, just this recursive law. Because we can create from lower level, very bottom level spans, he can create the score of higher level spans. So it's a recursive law. That's why, and we love recursive law and dynamic programming in computer science. So this is a bottom-up charter decoder. So to parse the full sentence, we compute as best using bottom-up chart decoder. Then traverse back pointers to recover the tree achieving that score. Nodes assigned the empty label are omitted during the reconstruction process to obtain the full n-ary tree. The overall complexity of this approach is order of n cubed plus ln squared, where n is the number of words and l is the total number of labels. We note that because our system does not use a grammar, there is no constant for the number of grammar rows, multiplying the order of n cubed term as in traditional CKY parsing. In practice, however, the order n squared evaluations of the span scoring function corresponding to order of ln squared term dominate. So the training that we want to use, we use a constraint, because we want at the next iteration, because we know the gold answer. The gold answer is T star. So we are using the hinge loss. And so if you want to understand this, of course, I assume that you know support vector machine, the idea of hinge loss, and all of those things. But if you are not familiar with that, start from this one, which is even more general than support vector machine. This article, more than 1,000 citations, I guess.